Our next topic is going to be a channel-related one, something that you don't normally care about in most wireless communications, but can be actually very important in satellite communications. That is the concept of Doppler shift. It can degrade your signal, but it can also actually provide some interesting information as well. I'll show you an example of that at the end of this discussion. So imagine, if you will, you have an antenna that's receiving a signal from a satellite. The electric field washing over this antenna, as we are all now very familiar, takes a common general form. It's going to be E vector phasor, an amplitude, a phase, and a polarization. I just lump it together in an E naught vector. It's complex. EXPJ, some sort of phase, starting phase, and then my wave number k, which is 2 pi over lambda, and then a unit vector that points in the direction of propagation. Now, at any given moment, let's say that receiver is in motion. I'm driving around on planet Earth, and I've got my antenna is a satellite handset. Or we could just be an Earth station, and this is not a geostationary Earth orbit satellite, and the physical rotation of the Earth is imparting some velocity to your receiver. Over a brief period of time, we can model this, regardless of how crazy you're driving, as linear motion, simple linear motion. So what does that look like? Well, I have a vector r that's going to be my position, and that's going to be equal to some velocity vector. So I have a direction and an amplitude, the speed, times a scalar time. Something you learned in high school physics, probably. So if I want my electric field as a function of time, I simply plug this into here. And out of the plane wave physics pops something interesting. Wherever the direction of propagation is, dotted into my velocity vector times time, that imparts a temporal variation that I did not have before in the phase as a function of space. Okay, let's go ahead and turn this into the time domain so that we can really see what's going on. How do I convert a phasor into the time domain? Well, I take my phasor. Just because my phasor has a function of t doesn't mean it's in the time domain. It simply means that amplitude and phase are changing as a function of time. I still have to add my carrier back in. EXPJ 2 pi f carrier times time. And I take the real value of this. This puts it back in the time domain. So that becomes the real value over here of E naught EXPJ, some phase theta naught minus 2 pi lambda k hat dotted by velocity vector of my receiver plus 2 pi fct. This is a complex exponential, but I really know that I can write it as the cosine of the argument plus j sine of the argument, which is Euler's theorem. This is going to disappear in the real value operation that I take. So I'm going to look like at the final end is going to be something like this. A field strength, a polarization vector, some arbitrary phase, phi naught or phi naught prime, if I want to put the phase of here into here, minus j pi lambda k hat dotted by v there. And I can even factor t out of here. And what I find is I have 2 pi times k hat dotted into velocity over lambda with a minus sign in front of it, plus my carrier frequency times time. And so what happens is motion in the presence of an electromagnetic field that is time harmonic, or at least carrying narrowband information, appears as a shift in frequency. In this case, I need to know what the direction, it could be a positive or a negative shift, right? I've got a negative in front of it, but the polarity of this term ultimately resides in whether the k naught is dotting with the velocity vector that could produce a positive or a negative, right? And so if I were to draw this and try to do this, compute this with scalars instead of math, I have an angle here that I'll call theta sub r. And I'll have a velocity vector v sub r here. So my shift in frequency is now fc minus, when I dot, if I take v and normalize it, I can pull out a v over lambda. And now what I'm left with is k hat dotted by v hat. Unit vector pointing in the direction of propagation dotted with unit vector pointing in the direction of travel. I know that that's actually a cosine of that angle. I can replace this using vector geometry with cosine of theta r. And of course, this is the velocity of the receiver. We haven't imparted any motion to the transmitter yet, but we will. And in fact, that's actually easy to do. If the satellite is traveling here, you can work through the exact same analysis. And you look at the direction of travel relative to the angle of the velocity. Make a theta sub t and a v sub t. You get the exact same formula. The only thing is that the polarity changes. Well, does that make sense? Okay. Well, if v is pointing in the direction of the propagation of the plane wave that strikes this antenna, then they're going to be aligned, which is going to give me a nice large positive result. The biggest positive result I can possibly have, VR over lambda times 1. Cosine of 0 is 1. And I'm going to subtract that with the carrier frequency. Well, that kind of makes sense, right? If you view this wave as an electromagnetic wave that's doing so many cycles per second, and I'm running away from that wave, it's going to appear that I'm receiving fewer cycles per second. It's like I've lowered the frequency of the system. If I turn around and flip the polarity, then this sign flips, and I'm marching, charging into the wave, and I see the cycles faster and faster. That's one way to rationalize this. And the sign changes opposite for the satellite because the wave is going away. If the satellite is moving in that same direction, it should be causing the equiphase fronts to bunch up as if it was a higher frequency of electromagnetic radiation. And so this is a really helpful general formula. And in fact, the maximum possible Doppler shift is going to be in either direction, positive or minus, VR plus VT over lambda. What are the units of this? Recall meters per second divided by meters. That gives you per second. That's hertz. That's hertz. And notice that it scales with wavelength. The higher in frequency I go, the bigger the shift. Okay. So let's put some numbers to this phenomenon. Why do we care about it in satellite communications? This is important. Let's say I have a GPS satellite. GPS satellites at a radius, they orbit at a radius of about 26,500 kilometers. If I go back to the very first week of this class, and I take the square root of Kepler's constant for Earth divided by that radius, I get the velocity of a circular orbit, which is 3.9 meters per second for this particular satellite. 3.9 kilometers per second. It's about 4,000 meters per second. That's really fast relative to Earth-based distances, right? Now, just to bound the problem, let's assume that I'm moving directly away from this satellite, that I'm on Earth. Yeah, I'm going to have some residual velocity, but let's pretend it's zero, because it's not nearly this fast. And let's assume that I've got the maximum possible Doppler shift. That's actually hard to do geometrically with a circular orbit, but this will at least bound the problem and give me an order of magnitude estimate of what's going on. So let's see. This results, what frequency does GPS transmit at? 1575 megahertz. And here the wavelength is equal to about 0.19 meters. The Doppler shift, the maximum possible Doppler shift in this scenario is the velocity divided by wavelength plus or minus, which is about 20.4 kilohertz. That's a fairly sizable shift. It's a voice channel in cellular communications in many instances. That's a significant chunk of bandwidth. Now contrast that to what we would consider mobile communications down here on Earth. Let's do a little comparison. On Earth, let's say you are riding a bullet train. At 200 kilometers per hour. If you convert this into meters per second, this is about 55.6 meters per second. And you're talking on your handset, let's say you're using the upper bands of about 1900 megahertz on your cell phone. In this case, your lambda is equal to 0.16 meters. A little bit shorter than the GPS example. But in this scenario where you're talking to a fixed base station on Earth, this is one of the more ridiculous speeds that you'd probably try to communicate with it. What would your Doppler shift be? (352 hertz). You're 2 orders of magnitude off compared to this run-of-the-mill satellite example. That's profound, isn't it, right? This is why we care about Doppler shift, and you probably have never talked about it in your mobile communications class, right? Because satellites move so much faster, if they're not in geostationary Earth orbit, than your typical transmitter or receiver pair, that it makes significant changes to how you track it, which means you've got to put more guard bands on your filters. You've got to put more guard bands on your frequency division multiplex channels. And there are extreme examples of where this has really bit people. So, for example, there was a mission a while ago, I forget which one, it might have been Galileo, the one to Jupiter. Jupiter has a huge Keplerian constant. So when you establish an orbit close into Jupiter to observe it, you're really cooking. You're like flying around that thing really quickly. And the differential in the Doppler from seeing a spacecraft going towards you around Jupiter as opposed to going away can lead to much larger shifts than this. And so there's a famous story about a European research team that was helping out with the NASA mission, and they actually designed the decoder and built the decoder receiver for this satellite. And they forgot to take into account the Doppler shift. Oops. So not only were things shifting to the left and to the right way more than the specification was calling for, but they actually were having problem with the dilation of the bits. Like there was the bits were so dilated in time going to and from the satellite that it exceeded the spec from what they were expecting their bits to look like. They were expecting everything to be rigidly timed to fit into these well-defined windows in time. They had really nice frequency standards on board the satellite. But of course, frequency standards are nothing when you've forgotten to take into account satellite Doppler. So you should always be aware of Doppler in the background of your calculations, just to make sure that you're not exceeding the spec and getting hundreds of megahertz of Doppler shifting around Jupiter. Now, that's a very pessimistic view of Doppler that I just gave. Is basically something you need to avoid. But Doppler also does some really interesting things in satellites that you can take advantage of. For example, we had an entire search and rescue satellite system up until recently that operated on the principle of Doppler. And it was called the SARSAT system. In fact, I think they still operate some of the satellites on this. It hasn't been completely decommissioned. They're always threatening to, but it still serves a purpose. SARSAT stands for Search and Rescue Satellite Aided Tracking. And it was established in about 1982. There was a famous case of a senator that was on a plane up to Alaska, like a little Cessna or something. He was flying with some people up to visit someone. I think it might have been a senator from the South. I can't remember. But anyway, they were on a visit to Alaska, and the plane went down. And to this day, we have never found that plane. Because Alaska, of course, is a vast wilderness. It's difficult to search. And frankly, there are a lot of places on Earth still today that you can crash into, and we will never find you. They're just sparsely populated. And so this system was then designed and pressed into service to try to find and rescue ships and planes in distress in remote parts of the world. Now, if you think about it, this is a very different problem from the GPS problem that we normally think of today. You're not saying, hey, where am I? You're basically telling somebody else, hey, I need help and you need to find me. That's a different type of location problem, which is why you need a different solution. Now, ultimately, the systems have gotten so sophisticated nowadays that the search and rescue satellites actually expect you to be able to lock on to a very high-fidelity GPS signal, or at least do enough signal processing to pull it out and transmit your coordinates back. There are still some scenarios where that's not possible, but GPS receivers have progressed remarkably, even in the last 10 or 15 years, to the point where we're getting a lot more confident in just doing a GPS-only fix on something. But, especially in the 80s and 90s, you had it was unlikely to get a good fix based on GPS alone. And, of course, you still have to relay that back to some help somewhere. And so this was the technique that they came up with. There is a system, I believe it was at least 3 low Earth orbit satellites that constantly went over the Earth in a retrograde orbit. So 3 retrograde low Earth orbit satellites at an altitude of 850 kilometers. The inclination It's about 99 degrees. So if you imagine the Earth is rotating like this. And normally you would, if you had a zero inclined orbit, you would launch your satellite, and the satellite would travel like this around the Earth. And let's see. Now, you flip it. Let's see if I get the inclination right on that. You incline this so that it is almost polar. Almost polar. And let's see. I got my rotation wrong. So what should be happening is it should be coming down this side. Maybe it's 81 degrees instead of 99 degrees. But in any event, you've inclined it past the poles so that as the Earth turns, you're now making almost a straight drop down the surface of the Earth. In fact, if you were to look at the ground track of the satellite, so the surface of the Earth is rotating and it's moving this way. And now I have this angled drop where I'm mostly going down, but I'm going a little bit forward too. I've exaggerated the angle a little bit. So effectively what happens is that the horizontal component of your velocity is almost matched to the Earth. And so for most of its drop around the Earth, this satellite appears to be riding a longitudinal line across the face of the Earth. Then it comes back the other side, and it does the same thing. Rides a longitudinal line back the other way. So, what does that do for you? Well, if you are an aircraft in distress, you have something called an emergency EPIRB, emergency position indicating radio beacon. It's something that you can activate or sometimes even activates automatically. If you have like a life raft and you inflate it and you put it in the water, the EPIRB will sense the water and it will start transmitting. It's got a serviced battery that will hopefully hold charge until the next time you service it, and then will power the radio for a brief period of time, enough to locate you. So these are called EPIRBs. The classic SARSAT ones operate at a frequency of about 406 megahertz. So in the UHF band. And think about what would happen here. The satellite, if I'm looking down on the Earth, let's say the crash is over here. So as the satellite drops down a longitudinal line, what does it see? Well, it sees this beacon transmitting at 406 megahertz, roughly. But there's some Doppler shift as well. And so over time, if it measures the frequency of the transmitted signal, we'd expect it to be centered at 406 megahertz. However, it's going to start off, as the satellite is up here, moving closer to the EPIRB. It's going to have a positive Doppler shift. And then, when it gets normal to it, the direction of propagation and the direction of travel are orthogonal, so that should eventually lead into no Doppler shift. And then it should start to drop as you pull away overhead. And so if you look at that inflection point, which should be exactly 406 megahertz, you can figure out what the latitude of the beacon is, just from looking at the Doppler shift. It's the exact same principle as going to a race car event, right? And sitting in the grandstand. You hear the natural whine of the engine. And what is that? It's got a pitch. It goes, and it starts off high, right? As they're coming around the track towards you, and they're going really high, and then all of a sudden they zip on by and they go, meow. You like the sound effects? That's good. That's exactly what it is. It's a Doppler shift. Starts high, ends low. The inflection point occurs when that race car is right in front of you. Basically the same latitude as the satellite. Now, would anybody like to hazard a guess? How would you figure out the longitude of the crash site? Well, the inflection point tells you where the latitude is. The longitude is roughly, you can back solve it from the slope of this curve, right? So think about it back in the race car analogy as well. If you had front row seats, and you were bending down and you saw the car whiz by, you would hear, it would be a very steep transition. If you had the cheap seats, and you were way back in the back row looking at binoculars, you would just hear, These are the kind of seats I always buy at a sporting event. And in that case, you'd see much more gradual. Why? Well, remember, I've got an EPIRB here. I've got a satellite that's up in the air, 700 or so kilometers, 800 or so kilometers, running by like this. If it's directly beneath, that's like being in the cheap seats. The angles change more quickly as I'm overhead, right overhead, traveling at the same speed. If it's over here, it's a much more gradual change. And I can just use basic math and trigonometry to figure out roughly where that is. And if I've got several of these satellites orbiting the Earth simultaneously, I believe they can make about 15 orbits during the course of a day. It doesn't take me more than an hour or two to read any EPIRB that happens to be on the Earth. In fact, there's usually kind of a helper system. There's a higher Earth orbit satellite that listens for EPIRBs, kind of gets a rough area, within a few hundred kilometers on Earth where this thing, EPIRB is, and then alerts the SARSAT satellite that's nearest to that area and then tries to triangulate it using the Doppler shift. Now, of course, what might be one of the natural problems with triangulating longitude and latitude in this particular fashion using Doppler shifts? There's an ambiguity here that should jump out at you if you're on the poles. Well, what's going to be the difference between the Doppler signature of an EPIRB here or one over here? I mean, this could be hundreds of kilometers at this point. Yeah, well, there's no difference. You would see the exact same Doppler signature from the mirror image on the other side in time. And so you may actually have to use several passes of a satellite to really resolve that ambiguity. More often than not, there's some other contextual information you can use, like the rough triangulation of the higher Earth orbit satellite, or some clues about maybe where the flight was last, or what have you. So it's not perfect, but it's actually surprisingly good. And I think even when that Malaysian airliner went down last year, I think one of the ways they defined the search areas was actually looking at some of the Doppler shifts on the pings that thing was sending up sporadically from like the engine beacon, looking at Doppler shifts and trying to reproduce its path. They're turning the data system into its own little SARSAT system.